All right, let's look at another rational function graph. If we have f of x equals x squared minus 4 over x minus 2, as usual, we're going to factor the numerator and denominator of this rational function. Hopefully you noticed that the numerator can factor in a difference of squares of x minus 2 and x plus 2. And look at this one. This one happens to have a factor that can reduce. Do you remember what that causes? It looks like there is a hole in this graph at x equals positive 2, right? So I know that there's going to be a hole in this graph somewhere at x equals positive 2. Now, if I reduce and I come up with a new similar function with the factor that's left over, I know that there is a graph of y equals x plus 2. It's the same exact graph as my original graph, just without that hole, right? And so if I want to figure out where that hole is at, I can take that function and plug in x equals 2 to figure out where my hole is in that graph, right? So if I plug in 2 plus 2 is 4. And so I know that there is a hole in my graph at 2, 4. 2, 4, I know that there's going to be a hole there. All right, let's keep looking at other pieces and other characteristics. It looks like there's no vertical asymptote, right? Because there's no other x value that's going to cause that denominator to equal 0. So no vertical asymptotes here. What about horizontal asymptotes? It looks like the degree of the top is 2, the degree of the bottom is 1. That means in this case, P is greater than Q. And if P is greater than Q, then there is no horizontal asymptote, or there actually happens to be a slant or oblique asymptote, right? Now, I can find the slant and oblique asymptote by dividing the numerator by the denominator. When you do that, this is kind of actually what we did up here. We divided, we reduced, and we ended up with this y equals x plus 2. What that means is that is the equation of my slant asymptote, right? It also happens to be the equation of the graph that's left over that just doesn't have a hole in it. So we can use that to actually graph our original function. We know that our original function is going to be the same exact picture as this y equals x plus 2. And so I know when I graph a line that the y-intercept, that b is at 2, the slope is 1, so up 1 over 1, up 1 over 1, down 1, left 1, and I can graph the equation. This line with the hole is the graph of my original function. The line y equals x plus 2 is the graph of the line without the hole, but I want the graph that has the hole in it because that was my original function. It kind of goes along with that slant asymptote as everything's kind of slanted and it's not going to kind of skew the other direction, right? And so this is the graph of this function, f of x equals x squared minus 4 over x minus 2. All right, let's do one more in this video. Let's look at D. When I'm looking at D, the first thing again I want to do is I want to factor. But be careful, that numerator looks like it's a difference of squares, but it's not because of this plus sign. So it looks like on this one, I can't factor it any farther than it already is. Which also looks like I don't have anything to reduce or simplify, so this is in most simplified form, meaning that there are no holes in this graph. There is, though, a vertical asymptote on this graph. It looks like at x equals 2, right? Looking at my degree of my top versus my degree of my bottom, it looks like I have a degree of 2 versus degree of 1, and so P is greater than Q. If P is greater than Q, then there is no horizontal asymptote, or there happens to be a slant asymptote. As x approaches negative infinity, my graph's not going to get stuck. It's going to either keep going down or keep going up. Same idea as we approach positive. As x approaches positive infinity, my graph's going to not get stuck at a horizontal asymptote. It's going to keep going up or keep going down, right? Depending on your graph and your values. So let's actually find that slant asymptote. Let's take our numerator, our x squared plus 1, and let's divide it by our denominator, our x minus 2. And using our long division from back in the day, x times what gives us x squared? So I have an x. So x times x is x squared. x times negative 2 is negative 2x. Remember, when we're doing our long division, we look for remainder. So what's the difference? Subtracting all of the terms. I end up here with a 2x plus 1. So now let's do that same process again. What times x gives me 2x? So I get 2. 2 times x is 2x. 2 times negative 2 is negative 4. And let's look for a remainder, the difference. When I add them together, I have a remainder of 5. But remember, when we're looking for slant asymptotes, when we are looking for slant asymptotes and we divide, we'd end up discarding the remainder and we just look at the major part of that function. So y equals x plus 2 will be my slant asymptote. So let's start graphing all of these characteristics. We have no holes. We have a vertical asymptote at x equals 2. We have a slant asymptote at y equals x plus 2 with a y-intercept of 2, a slope of 1. And so I'm going to have a slant asymptote that looks like this, right? All right. So now it might be helpful to look at x and y intercepts because I have a bunch of little quadrants here and I'm not sure where my graph is actually going to go. So let's pick out and try to find our x-intercepts and y-intercepts so it might be more helpful to figure out where the rest of the graph is placed. Let's find x-intercepts by plugging in 0 for y. When I plug in 0 for my f of x, I can set the numerator equal to 0 and solve. When I subtract 1 from both sides, and then I square root a negative number, we get imaginary numbers, and so there are no real x-intercepts because we're not talking about graphing on imaginary axes. We're just talking about the regular real number system. So there are no real x-intercepts. So let's look at y-intercepts. In order to find our y-intercepts, we're going to plug in 0 for x. If I plug in 0 to the numerator, I get positive 1. If I plug in 0 to the denominator, I get negative 2. So it looks like there's a y-intercept at y equals negative 1/2, which is about right there, right? So this kind of gives me a good idea that I am going to kind of swoop this way and not touch that slant asymptote, swoop this way and not touch the vertical asymptote. But now you might want to plug in other values to help us figure out what's happening on the other pieces of this graph. So test, I don't know, x equals 4. If you plug in x equals 4, 4 squared is 16 plus 1, that's 17 on the top, right? If I plug in x equals 4 to the bottom, 4 minus 2 is 2. And so I know that I have positive values that are above here. Let's see. And then I'm going to go ahead and graph it above my values, right? And so making sure that I don't touch my x-intercept, making sure, or vertical asymptote, and don't touch my slant asymptote, the graph of the function, the sketch of my graph looks something like that.